Alrighty, good morning. Happy April Fools. Oh, hang on. Just getting everything set up in here. All right. Good morning. Ooh.
Alrighty, good
morning. Oh, shoot, hang on. That always surprises me when I start talking and then I hear the delay coming through and I hear what I said just a few seconds ago. All right. Well, happy April 1st. I don't know how easy it is to pull off April Fool's jokes digitally, but I promise you that I'm not going to do any. Okay. All right. We already have. Okay. Hey, Winnie. So I already have in the comments. We have our first question about the test, and so here's the deal. So it's if things had gone according to plan, you would have all been finished with it by now. So I was planning on having the test done before we had a lecture section together, but as you already know, that's not the case. The exam due is at 12. So before we talk about the test at all, we're gonna get through lecture first because we have, material to cover and a schedule to stay on top of. Then at the end, here's the thing, and I expect that after I say this, my the concurrent viewers may drop from 7 down to 0, but I can only answer specific kinds of questions about the test, and I'll elaborate that. What I mean by specific kinds of questions are, for example, there was so as you know, there's multiple forms of the exam. They're not all identical, and on one of them that went out, it was brought to my attention last night that there was a sorry, I can almost speak. There was a suspected typo, and I looked at the exam. Turns out there was, on one specific problem on one of the versions of the exam, there was a typo. So I contacted every human who had received that version of the test via email last night to let them know that there was a typo on the exam. So if the question is there a typo on problem 6? I can answer those questions. Questions like, how do I do this? I don't know where to start. Those types of questions I won't be able to answer. So I'm willing to take the questions at the end of lecture. I don't know how useful I'll be able to be, because my input on the exam, on this particular exam, is going to be as helpful as my input would be if we were all sitting in a room taking a test that was timed. That being said, this exam was written with the intention it was written as an open book, open internet, and open other humans. It was written under the assumption that you guys would be talking to each other, figuring things out together, helping each other. Peter, you cracked me up. The honest answer, if Peter asked me, what's the answer to question 3? The honest answer at this moment in time is I don't know, actually. Because on 2 counts. 1, I don't know what version of the test you have, and 2, even if I did, I don't remember the numbers. So I am a blank slate there. Anyways, what was I saying? Right. So open book, open internet, open other humans. This exam was written with the assumption that you all would be talking to each other And you don't need to think that talking to each other, meeting for a Skype or Zoom hangout to like, okay, let's go over the test together. Let's like, how are you guys handling problem 3, for example, Peter? You can, use all the people, Raj. Exactly. Like collaborate with each other. Even if you have different versions of the test, be like, okay, I've got a problem that's going like this. And I think it might have to do with these 2 things, but I'm feeling a little stuck. Totally bounce ideas off each other. Take this collaboratively. It was written with that in mind. Not just that in mind. I'm intended. That makes me sound like I'm a Victorian person about to get married. I intended for you guys to collaborate while taking the written portion of the exam. So the multiple choice was kind of going to reflect everybody's knowledge individually on simple problems, and then these more expansive problems were designed for collaboration. Since the exam is open to other humans and you count as human, wanna help me out? Salvish, that is a great question. But you actually made a critical mistake, but paid me a compliment. Turns out I'm actually an android. And since you think I'm human, that means that I just passed the Turing test and more models of my AI software and hardware will go into production. Okay, Winnie, have you looked at our test scores? I have not looked at your test scores. I've not looked at the test scores yet. Yeah, I'm kind of waiting till they're all in, and then I'll take a look at them and see how things went. What I can say about the multiple choice exam is the problems were all modeled after problems that you'd run into on the ACS final, and or the simpler problems that were that can be found at the end of each chapter in the Tro textbook. So Raj, it looks like you want less time on the multiple choice. I think you should look at them. At the multiple choice. Oh, the scores. Winnie, don't worry. I totally will. I'm just waiting till I can look at all of them. Because the problem with any sample size is how representative is it of the entire body of work, and not the body of work, of all the. Oh my goodness, I'm having such a hard time using words today. The problem with looking right now is I won't see all of them, and so with looking at selected scores, I won't know if they're representative of the entire group. So once everybody's scores are in, I'm going to take a look and figure things out from there. Totally. So I will eventually, but now is not that time. Raj, you want more multiple choice questions? I think you have a whole ACS study guide filled with them if you're really desperate for some. Oh, the scores are really good. Tommy is telling me the scores are really good. That's tempting me to look at them. But wasn't it due yesterday? Well, so if you look at the... so Winnie, wasn't it due yesterday? If you look at the announcement, because I was late posting them and making them available, I extended the deadline so they weren't due by midnight last night. They're due by midnight tonight. So... because I believe, I can't remember exactly when the quiz went live. I know the exams got emailed out at 2 p.m. So I just made the deadline for all of them at 11:59 tonight. Let's see. Selected score, going to represent the entire class. Yeah. No, I know Frage once more time. I was just being cheeky. So, So, okay. So we can maybe do more, test test talking. Okay, so sorry, Tommy. You're okay. That made me laugh. Sarcasm. One of the hard things about sarcasm is it's hard to communicate without tone of voice, and there is no tone of voice on a text thread, right? But that second answer cracked me up. Multiple choice isn't due till today. Yeah. And I posted, I believe I posted an announcement on Canvas saying that the due date for everything was extended till 11:59 p.m. Today. And if you look at the quiz and you look at when it's open from, the quiz closes at 11:59. Yes, totally. Okay, so let's see. Salvage. I was at the exam and stuff for more than 11 hours yesterday because I thought it was due tonight. Time to uninstall Life. Yeah, it sounds like you might need to. This is not an April Fool's, I promise. Salvage, it sounds like you may need to shut down, reboot your operating system. Yeah, rather dry over text. Sarcasm is rather dry over text. Yeah, no. All the exams are due by 11:59 tonight. When I last checked my email, I don't even know why I was up at midnight. Yesterday was a long day. I last checked my email around midnight, and so far I had only received one exam submission. So if you've already submitted the written test, but you want to look over problems, you totally can still send it in. If you want to revise stuff, check stuff, send in a different version. If you've already submitted, again, last I checked, only one person had, but that's fine because it's not due till today. I'm going to write myself a note. I'm going to post this to Canvas. Canvas post. Alrighty. So it's just the Canvas saying that. Okay, so yeah. If you've already sent in your exam, it's not due yet. So if you want to look over it, make changes, you can resubmit it, and I will. The one that I grade will be the one that's submitted most recently, and I'll make a post to Canvas with those details. In your Canvas, it said that only the take-home is due today, and the multiple choice was due last night. Really? If so, then I posted in. Then there's an error, because if you look at the quiz. It's on Canvas. If you go to quizzes and look at the multiple choice exam, it says that it closes today. So today is the date that I set for it. It's possible that I posted an error. I'm not exactly sure. You're making me doubt myself. But okay, we've got confirmation. So it's possible. Can we take the ones more? Well, no, unfortunately not. But don't worry, I will totally make you a brand new multiple choice exam to take when exam 3 hits a little later this semester. Because then the people retaking it would have an unfair advantage over the people who have not taken it yet. All right. Okay, we'll do more exam convo at the after we finished lecturing. Before we dive in, our song of the day is "Touch Me and I'm Gonna Scream." Touch me, I'm going to scream. This is by My Morning Jacket. Yo, Sophs, can you guys not come around this side thing because the noise breaks in? Thanks, babe. All right, by my morning jackets. There we go. Is our song of the day. Check it out. I will link in the description. Okay, let's see. We got a cascade. Canvas that says do 3 3 Canvas same. Okay, I will check that situation out. But at this moment in time, we are going to push through to lecture. All right. So we on Monday began a discussion of electron configurations, and excuse me. We started talking about electron configurations, and we left off right at the moment where we had introduced the idea of the, excuse me, I've got hiccups all of a sudden, Nobel gas abbreviation for electron configurations. All right, and the basic idea, and you can rewatch the video from Monday's lecture if you need to catch up. But the basic idea is if you look at neon has 10 electrons. Here, I'll just write out the electron configuration: 1s2, 2s2, 2p6, and compare it to sodium, which has 11 electrons. It's 1s2, 2s2, 2p6, 3s1. We said on Monday that you'll notice that neon and sodium, or I should say not neon and sodium, sodium has all the electrons that neon has, plus one additional electron. And it's almost like sodium has an atom of neon, at least electronically, contained inside of it, plus just a little bit extra. And as a result, we can use, or it's an accepted formalism to use our noble gases to abbreviate our electron configuration. So we can write the electron configuration of sodium as a bracketed neon, followed by 3s1. All right. This is the noble gas abbreviation. Right here. That's what it's called. Noble gas abbreviation. Oh, sorry. Here my my 1.5-year-old was shrieking in distress. Sorry about that. But he's okay. Okay, anyways, this is called a noble gas abbreviation. We use it to simplify, so that we don't have to write as much. It simplifies the whole electron configuration writing situation. It makes it a little less intensive. Now, the question is, or not the question, but where we're headed with this is the noble gas abbreviation is awesome, but you may be going, well, if I didn't know what the electron configuration for neon was, I wouldn't know to use it for sodium, right? So does this require me to memorize the noble gas configurations of or the electron configurations of my noble gases? And the answer is no. The beautiful thing about the noble gas abbreviation is using it comes as a direct consequence of the periodic table. The periodic table essentially gives this to you. And I'll show you how to use the periodic table to write out electron configurations. Much faster than counting individual electrons, placing them in individual orbitals. All right, now before we do, we need to spend a moment reacquainting ourselves with the periodic table. All right, which I have right here. All right, now, a couple things. First, something to keep in mind with the periodic table is we need to remind ourselves of our blocks. And this is something we talked about at the very beginning of lecture. Actually, I'm going to center this guy. At the very beginning of class this semester, we talked about the different blocks of the periodic table. So I want to spend a minute kind of reacquainting us with those. We introduced them, that there's the S block, P block, D block, F block, and we said we won't be using this till later. Well, now is later. So first off, the periodic table can be divided into blocks. And those blocks are here. So we have this right here, the first two columns. This is known as the S block. All right. Down here, this is the D block. All right. Over to the right, this is the P block. And then down floating underneath, we have our F block. All right. And knowing which block is which is super helpful for writing electron configurations. And this is why. The block, so the block an atom falls in, tells you the subshell. Ooh, it's weird. Tells you the subshell of its highest energy electron. All right, that is the first thing that the periodic table tells you. The block that contains an element tells you the energy level of that particular element, the subshell of that particular element's highest energy electron. It tells you something about the valence electrons. All right. And you can ascertain that by looking at the block of the periodic table. Next, the next thing we want to pay attention to on the periodic table is the period. Oh, that is my dog. He's found something interesting. Now, the period, when we talk about periods on the periodic table, we're talking about columns. No, we're talking about rows. Excuse me. That is one of the many ways dyslexia makes life fun. When we talk about periods on the periodic table, a period is equal to a row on the periodic table. And you can number the rows moving down the periodic table. This would be 1, 2, 3, 4, 5, 6, and 7. All right. So that is, we would refer to this as the first period, second period, third period, etc. And the reason why this is significant is the period an element falls in tells you the shell or energy level, right? It's honestly the weirdest N I've ever drawn. Let's do better. Tells you the shell of its highest energy electron. right? So knowing the block that an element falls in and the period an element falls in will tell you the energy level and the subshell, the shell and subshell of its highest energy electrons. And here's why knowing that is clutch for writing an electron configuration. All right. So here's how this is useful. Let's say I want, let's say I ask you to write the electron configuration for the following elements. All right. Let's say I want you to write the electron configuration for nitrogen. Oh, let's go with phosphorus. We've already done nitrogen. All right. Now here is how you use the periodic table and the noble gas configuration to write your electron configuration super fast. You'll notice that phosphorus is right here. It has 15 electrons. And so using the method that we were using on Monday, we would have to count out all 15 electrons, place them in shells and subshells and move on up and all that business. Here's how you use the periodic table and the noble gas abbreviation to fast track this process. So first what you want to do, hang on, getting tangled in my own wires. Okay, so the first thing you want to do when you're doing this, step one, is you find the atoms nearest noble gas. Hang on. Correcting dyslexia as we go. Nearest noble gas with fewer electrons. All right. So step number one is we need to find phosphorus's nearest noble gas with fewer electrons. And that would be neon. Right? Neon has 10 electrons, phosphorus has 15, argon has 18, so neon's our nearest noble gas with fewer electrons. That is going to be where we start writing our electron configuration. Because neon has fewer electrons, that means phosphorus has all of the electrons of neon plus a few extra. All right? Step two. Identify the period. So identify the atom's period. And count your way over. All right, what do I mean here? Identify the atom's period and count your way over. I'm actually going to change my color. So phosphorus is right here. You'll notice that it is on the third period. To identify a period, you just count your way down from the top. And phosphorus's period is the third. All right? It's the third period in the P block. All right, so to get to phosphorus, we need to first, I'm going to scoot these guys over just a little bit. We start right here, and we're going to count our way over. And you'll notice that first, we go 1, 2, 2 spaces through the S block. All right, so this will result in 3s2. All right, because to move through to phosphorus, we've got to move through the S block And then we go 1, 2, 3 more spaces into the P block to get to phosphorus. So the electron configuration here will be 3s2, 3p3. All right? And these electrons here are our valence electrons. All right? And that's how you use the periodic table with the noble gas abbreviation to rapidly spit out your electron configuration. You start by finding the atom's nearest noble gas. That's going to be the one you use to abbreviate. And then the second, you identify the atom's period, because phosphorus is on the third period. That means we're dealing with n equals 3. And to get to phosphorus, we start at the edge and move our way through. We move 2 spaces through the S block. So that means we have a full 3s subshell. And then to get to phosphorus, we move 1, 2, 3 spaces over to get to phosphorus. So we have 3 electrons in our p orbitals. Let's do another example. All right, let's write the electron configuration for fluorine using the noble gas abbreviation. All right, so first we identify where fluorine is and its nearest noble gas with fewer electrons. That's helium. All right, so we are going to give fluorine a helium with a bracket. All right. What about row 4? Okay, Macy, that is a great question. We will get there. We will get there in just a few examples. Totally. All right. So here we've got. So we're starting with helium. All right. Now we identify what period we're on, and fluorine is on the second period. All right. So that means we start here, and we got to move 2 spaces through the S block. So this will be 2s2. Then we move over to the P, and to get to fluorine, we have to move 1, 2, 3, 4, 5. Since we moved 5 spaces in, that means we're going to have 5 electrons in our 2p subshell. So fluorine's electron configuration will be 2s2, 2p5. So that is the electron configuration for fluorine. Let's do argon as our next example. Let's see. Oh, new. Okay, cool. Let's do argon. Now, argon is a noble gas. All right. So its nearest noble gas with fewer electrons would be neon. All right. So argon is going to get use a neon noble gas abbreviation. And now let's count our way over to argon. First, we identify that we are on the third period, starting from the very left-hand side. We move 2 spaces in. So this is 3s2. Then we move across to the P block, and we jump 1, 2, 3, 4, 5, 6. 6 spaces to get to argon. All right, so argon's electron configuration will be 3s2, 3p6. Cool? All right, now let's answer Macy's question. Let's do something on the fourth period. How about this? How about we do the electron configuration for calcium? All right, Calcium is right here. Its nearest noble gas with fewer electrons is argon, which means that we will give calcium. We'll use argon as our noble gas abbreviation. Calcium is on the fourth period. So starting from the end, we go 2 spaces, just 2 spaces in to get to calcium. That means that our valence electrons here will be 4s2, and that's where it stops because calcium is in the s block on the fourth period, so we know that its highest energy electrons are in the fourth shell in the s subshell. All right, now I want to draw your attention to something. But wait, I want you to recall the electron configuration for argon that we literally wrote on the previous slide. Argon has an electron configuration of neon's its noble gas abbreviation, 3s2 3p6. And you're like, yeah, that's what we wrote. I don't see the problem. Well, if this is the case, that means that we could write out calcium like this. It's all the electrons of argon, right? So it's neon 3s2 3p6 4s2, right? And you may be going, yeah, that's just because that's logic, right? It's all the electrons of argon, so it's argon's electron configuration plus 2 electrons in our 4s orbital. Now, here's the problem. Remember this little energy graph that we've been using. In the first shell, there's just the 1s subshell. In the second shell, there is the second shell has a s subshell and a p subshell. Now on the third shell, we have s, p, and d subshells. And on the fourth and final period, not the fourth and final, there are other, sorry, I even said period. There are other shells other than the fourth shell, but the fourth shell is where everything comes into play. There's the S subshell, P subshell, D subshell, and F subshell. All right. Now, I want you to compare the electron configuration for calcium and argon. Argon has its absolute highest energy electron in the p subshell. But then argon, the next electron we place so argon has its last electrons in the 3p subshell. The next electrons we place, however, in calcium are into the 4s subshell, not the 3d. All right? In calcium, we go up a shell, we go up to the fourth energy level, even though there's actually 5 available orbitals on the third shell. So the question is, why did we skip the 3D subshell? Why did we skip it? Because going off the periodic table, we ended up filling our 4s subshell before we filled the 3D subshell. Is this a mistake? No. This is the electron configuration for calcium. It's absolutely correct. You did write the correct electron configuration. But what happened is it turns out, so the answer to the question, why did we skip our 3D subshell? It turns out that, whoa, let's get rid of that squiggle. So the answer to that question is in the gas phase. It turns out that the 4s and the 3d subshells, orbitals, are very close in energy. And in the gas phase, it turns out the 4s orbital is slightly lower in energy than the 3d orbitals. Oops. So the 4s orbital is slightly lower in energy than the 3d orbitals, which is why, let's see, hang on. Which is why 4s fills, okay, here, hang on one second. You guys are being way too loud. Could you keep the volume down, please? Okay, awesome. Thank you. Okay, sorry. I am back. If you're wondering why there was very poor, almost drunken birthday singing going on, my youngest niece turned 1 today, and that is not an April Fool's joke. So anyways, that was going on in the other room. So, sorry, getting back to our lecture, the 4s orbital fills before the 3D. All right. And that happens where the 4s fills before the 3D. That also is true for 5s. The 5s fills before the 4D. 6s fills before the 5D, etc., etc., etc. This keeps happening, all right? And so we say that the nth s orbital fills before the n-1d. The d orbital will always be one energy level lower than the s. The reason why this doesn't happen before this moment in time is because there are no d orbitals on the first or second shells. But once you hit that third shell, you fill the 4s before the 3d and then the 5s before the 4d, etc. So they're very close in energy, but s in the gas phase is slightly lower. All right. Now, if you're kind of like going, dang it, this means that this is one more thing to memorize. The cool thing is you actually don't need to memorize it because you correctly wrote out, if I could draw your attention back to the previous example, you correctly wrote the electron configuration for calcium without even knowing that this was the case, right? You actually wrote the electron configuration for calcium filling, the 4s orbital first before you filled the 4d. And that's because the periodic table, you let the periodic table be your guide. It will fix that for you. So you don't have to remember 4s comes before 3d or 6s comes before 5d because the periodic table keeps track of that for you if you're using the method that I showed you, writing electron configurations with, the Nobel gas abbreviation. Cool? Okay, now let's actually, so we've done our first example on the fourth period. Let's do some more, and let's actually venture into the D block proper for the first time. So let's use, let's see. Let's do something fun. Let's write out the electron configuration for chromium. All right, so first we have to find chromium on the periodic table. All right, it's right here. Chromium's nearest noble gas with fewer electrons is argon. So we're going to be using argon in a bracket as our noble gas abbreviation. Next, we need to identify the period that chromium's on, and it is on the fourth period. All right, so we are going to start right here, and we need to count over to chromium. So first we go 2 spaces into the S block. So this will be 4s2. All right, but then you've got to remember this line right here is the start of the D block. All right. And when you look at, we filled our 4s orbitals. The D block, the D orbitals that we need to start filling now are actually our 3D orbitals. You'll remember those are the ones that got skipped over when we filled our 4s first. So when you cross from the S block to the D block, you're switching from here, in this case, in this problem, we're switching from n equals 4 down to n equals 3. All right, your energy level for your d orbitals will always be 1 level lower than the energy level of the s orbital you just filled. So we're going to start filling our 3d orbitals, and now we need to figure out how many electrons we're putting in. And to do that, we count over 1, 2, 3, 4 spaces over to chromium. So this is 4s2, 3d4. 4s2, 3d4. Because we know that our D will always be 1 energy level lower than the S we just filled. All right, 1 integer lower. Make sense? Hit me with questions if this is getting confusing. All right. Okay, let's do another example. All right, how about, let's do something fun. Let's do palladium. Palladium, that fun metal that gave Robert Downey Jr. purple veins in Iron Man 2. Let's find that sucker on the periodic table. It is PD. It's right here. Number 46. Its nearest noble gas with fewer electrons is krypton. Kr. All right. Now, we're going to use krypton as our noble gas abbreviation for palladium. Next, we need to identify the period we're on, and we are on 1, 2, 3, 4, 5. Fifth period for palladium. All right. So we start at the leftmost end. We need to count our way over, and we have to move 1, 2 spaces through the S block. So this will be 5s2, and then we remember that when we cross from S to D, we cross from, well, in this case, this problem, n equals 5 to 1 lower. We just filled the 5s, so that means we're going to start filling the 4D subshell. Now we count our way over to palladium. 1, 2, 3, 4, 5, 6, 7, 8. So this will be 4D8. Will be the electron configuration for palladium. 5s2, 4d8. All right. Okay, let's see. Let's do another example. All right, let's see. Okay. How about we do... Oh! Let's do this. Let's do antimony. Or as I like to call it, SpongeBob. Antimony, SB, is number 51. It's located right here on the periodic table. Our nearest noble gas is krypton. All right. So we're going to put Kr as our noble gas abbreviation. Now let's identify our period. We're down on the 5th period again. So starting from the very leftmost side, we count over 1, 2. So this is 5s2. And as we're already growing a custom, we're about to cross over into the D block, which will move us from n equals 5 to n equals 4. Our D energy level is always one lower than our S, right? So we've got 5s2, and now we have to count our way through the D block. Keep in mind, the D block ends right here, all right? So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 5s2, 4d10. We have a completely full D subshell, and you'll notice we're about to cross over into the P block. All right, we've never done this before. We moved completely all the way through a D shell, the D subshell, and then back into the P subshell. Now, keep in mind that our D orbitals are always one energy level lower than our S, but our P orbitals and our S orbitals will always have the same energy level. All right. So when you cross from the D block back into the P block, we're back on the 5th shell, because remember, for krypton, we completely filled up our 4s and our 4p. Before we filled our 4d orbitals, we went up, filled our 5s, went back down, filled our 4p. The next available energy level subshell is the 5p orbital. So now we have to count our way over to antimony. So this is 1, 2, 3. So this will be 5p3. All right. So our electron configuration here, 5s2, 4d10, 5p3. All right. That is the electron configuration for antimony. All right, the electron configuration for antimony. Hopefully, using the D block is kind of becoming more familiar with you. I want to pause and take a moment, because we've been focusing on the electron configurations. I want to pause for a minute and actually write out our orbital diagrams. Now, when you write your orbital diagrams, you go for the valence electrons. All right. That's one of the beautiful things about the orbital diagram, is that it's only focused on the highest energy orbitals. So you don't have to write out all the orbitals for krypton. You just have to write out the valence electrons from your electron configuration. So the electron configuration for antimony, for example, will be, we have our 5s subshell, we have our 4d subshell, which has 10 orbitals in it, and then we have our 5p with 3 electrons in it. All right, so our S subshell is full with 2 electrons. Our D subshell is also full with 10. You'll see that I'm filling everything with 1 electron first, because if electrons prefer not to share room. So I always put 1 in every orbital, then fill up the rest, and then we have 3 in the P subshell. 1, 2, 3. And that is the orbital diagram for antimony. All right, let's take a minute and actually go back through the previous examples we worked and just write out the orbital diagrams to get some reps in. Okay, so let's take a look at palladium. All right, palladium is going to have a 5s subshell, and then 1, 2, 3, 4, 5, 4 d orbitals. We have 2 electrons in our 5s subshell and 8 electrons in our d. So 1, 2, 3, 4, 5. All right. So that is the orbital diagram for palladium. All right, now let's take a look at the orbital diagram for chromium. All right, if you look at the electrons and the orbitals we have in play, we have our 4s subshell, and then we have our 3d, our 5 3d orbitals. And when you look at the electrons, I'm going to get a little color-coded here. We have 2 electrons in our 4s subshell, and we have 4 electrons in our d. 1, 2, 3, 4. All right, and this orbital diagram and electron configuration are both incorrect. You may be going, what? Yeah, this electron configuration and orbital diagram as drawn are incorrect. All right. Now the question is, why? Right? Why are these incorrect? Well, turns out something very special and unique happens when you have 4 electrons in a d orbital with parallel spin, something we call parallel spins. Four electrons with parallel spin. All right, that means that they are all oriented in the same direction. As you can see, as drawn, they're all pointing up. Now, we talked about last lecture, the reason why we make all of these electrons point in the same direction is because the spin represents the magnetic field generated by the electron as it moves through space. All right, and we all know that magnetic fields like to be oriented in the same direction, right? Magnets snap together a certain way. If you turn them, they'll snap back in place because they're at a lower energy state when they're all aligned. Now, when you have this situation where you have 4 electrons with a parallel spin, and this only happens for the d subshell, you get 4 electrons with parallel spin. The magnetic field, the strength of the magnetic field is so great that they can steal an electron from a lower energy subshell, steal that electron, promote it up into the higher energy d subshell, because having 5 electrons in a row, the magnetic attraction is so great that the electron can't help itself. So when you have 4 electrons with parallel spin, in the d block, what happens is the d steals an electron from the S subshell. So what happens is one electron from your 4s subshell gets promoted to the 3d subshell. So the orbital diagram actually, so the correct orbital diagram looks like this. We have our 4s, we have our 3d, and there will be one single electron in the 4s, and then 1, 2, 3, 4, 5 electrons in the 3d subshell. All right. So if this is the correct orbital diagram, that means that the correct electron configuration for chromium is, we still have our argon, noble gas abbreviation, 4s1, 3d5. All right. So this is the correct orbital diagram. This is the correct electron configuration. The thing to look for when you're doing an example, so when you're, so this is a wrinkle, right? This is an exception. And the thing to look for is when you are writing out the electron configuration, if you have a situation where you have four electrons with parallel spins, that is when you promote one electron from your S subshell up into your D. Cool? Let's do another example with this exception in mind. All right, so let's do, let's write the electron configuration for silver. It's a great metal used for killing vampires and werewolves, and also it's the metal that that earned me my dissertation defense, successful dissertation defense in grad school. So let's take a look at silver. Its nearest noble gas is krypton. All right. So we use krypton as our noble gas abbreviation. Now looking at the period we fall on, we are on the 5th period again. So starting from the very left-hand side, we move 1, 2 spaces in, so that's 5s2. We're jumping to the D block, right? So we know that our energy level drops down. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9 spaces in. So this will be 4d9, 5s2, 4d9, and now we move to write out the orbital diagram. All right, so we have, let's see, our 5d subshell, excuse me, or 5s subshell, and then 1, 2, 3, 4, 5, our 4d subshell. Now we have 2 electrons. 2 electrons in our 5s orbital. Now in our 4d, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, and you'll notice that I'm getting fancy with the colors here, and that is on purpose. All right, we're getting fancy with the colors, and here's the reason why. Remember what we said on in the previous example, that anytime you have 1, 2, 3, 4 electrons with parallel spins. 4 electrons with parallel spins, we're going to steal one of our electrons from the 5s subshell and promote it up into the D. So we're going to steal one electron from our 5s subshell and promote it here. So the actual correct orbital diagram will look like this. We'll have our 5s and our 4d. Now our 5s will only have one electron in it because it lost one, and our 4d will have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That 10th electron, again, coming from the 5s subshell. Well, if this is the correct orbital diagram, then that means that the electron configuration we wrote out at first was also incorrect. And the correct electron configuration for silver will have krypton as its noble gas abbreviation. Then it'll be 5s1, 4d, 10. All right. So this is the correct orbital diagram and correct noble gas abbreviation. All right. So you may be sitting there, you may be wondering, okay, how do we catch this? How do we find when we have to run it? Sorry. Let me try that again. You may be wondering, okay, well, now I'm a little paranoid. There's this weird exception out there. How can I tell when I'm going to be running into it, when I won't? Well, one thing to keep an eye out for is, like I said in the previous example and this one, anytime you have 4 electrons with parallel spins, then you will be promoting, 4 electrons with parallel spins in the D block. You'll be promoting 1 electron from your S subshell up into your D subshell. All right. But another kind of quick and easy way is to look at the your total D count. All right. Anytime you have, hang on. There we go. So anytime you deal with a situation where you have 2 electrons in the s orbital and 4 electrons in the d, and again, it doesn't matter what period we're on. If you have 2 in the s and 4 in the d, or if you have 2 in the s and 9 in the d, in both of these scenarios, you have 4 parallel spins, and you can see that in the previous 2 examples that we did. So you're going to promote 1 electron from the S subshell to the D subshell. So your S2D4 will become S1D5. S1D5. Your 2SD9 will become S1D10 every time. All right. The thing to look for is watch for 4s and 9s in the D block. Watch for D4 and D9. Any atom or ion that ends with D4 or D9 will steal 1 electron from the S block. All right, those are the things to keep an eye out. If that helps you, roll with it. If it doesn't, and you're more like me and you don't want to memorize 4s and 9s, you can always catch it if you write out the orbital diagram and then see oh, I've got 4 electrons in parallel. Let me steal 1. That can also be a reminder. So do whatever works best for you. Cool. All right. Let's see where we are. Okay. All right. So we have talked about electron configurations. We've talked about, how to write the electron configuration and orbital diagram for elements that fall in the S block, P block, and D block. But we have been ignoring the F block. All right, so what about the F block? All right, now, here's the thing with the F block. You'll notice, so this is, right, the F block down here. All of these guys that are kind of floating here. And you'll notice that something weird happens in the D block on the last two periods. On the sixth and right, 1, 2, 3, 4, 5, 6. Yep, sixth and seventh periods. Something weird happens right here. Right between lanthanum and hafnium, right between actinium and RF, which I don't happen to know off the top of my head what that dude is. And when I say something weird, I mean, look at the atomic numbers. They're right next to each other, but you jump from 57 to 72. Or, right underneath it, you jump from 89 to 104. All right, why is that? Well, oops. The reason why, so you'll notice there's that gap, right? 57 to 72 or 89 to 104. I actually need to erase. What happened? Why doesn't it go from 57 to 58? Well, the answer is it does, but 58 is actually right down here. It does go 57, 58, 59, 60, all the way to 71. But 58 to 71 is in the F block, all right? And the F block is 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 atoms long, all right? So what that means is the F block actually belongs in between 57 and 72 and in between 89 and 104 on the 6th and 7th periods. And before you can move from the first space in the D block to the second space in the D block, you have to first traverse the entire F block, all right? So what that means is it means you have to handle the Nobel gas abbreviation. You need to write the electron configurations like so. All right, so I'm going to open up a fresh slide to remove all my chicken scratch. So the important thing to remember is the F block starts after you move one space in to the D block on the 6th and 7th levels. So to kind of ease our way in, let's start by writing the electron configuration for lanthanum. All right, lanthanum, who's right here, has a noble gas abbreviation of xenon. All right. Now you'll notice that lanthanum we start. Oh, let me scoot my little period numbers over. Okay. So we start on, as always, on the very leftmost part of the periodic table. There we go. And we're going to count 1, 2 spaces in. All right, so this will be 6s2. We then move into the D block as we always do. So we know that the S block is energy level 6. The D block is energy level 5, right? So for lanthanum, our electron configuration will be 6s2. And because we only move 1 space into the D block, it'll be 5d1. And that is the electron configuration for lanthanum, number 57. Now, let's do CE. I think that's ceruleum, but I don't actually know all the names of my lanthanides and actinides. So that's a little bit of a guess. Let's do, I believe, ceruleum, which is number 58. Only 1 electron. It only has 1 more electron than lanthanum. Okay. So again, 1 electron more than lanthanum. It's still going to have a xenon core. We still have to move through the S block to get there. So we're still 6s2. We move 1 space into the D block, 5d1. But then you'll notice to get from lanthanum, which is 57, down to ceruleum, CE, we have to move into the F block, all right? And if the S block is n equals 6 and the D block is n equals 5, just like the D block is 1 energy level lower than the S block, the same thing is true for the F block. It is 1 energy level lower than the D block, all right? So it's 1 space into the D block, so this would be 6s2, 5d1, 4f1. All right, before we start filling our D block, we will fill our S subshell completely, so 6s2. We will put 1 electron into our D block, 5d1, and then we jump down to the F block. All right, if we wanted to write the orbital diagram, we have the 6s subshell, the 5d subshell, and then the 4f. 1, 2, 3, 4, 5. I'm gonna need to make some space here. 6, 7. I need to redraw my D's. 1, 2, 3, 4, 5. 5d. Then these are the 4f. So we have 2 electrons in our 6s, 1 electron in our 5d, 1 electron in our 4f. All right, let's do another example. The F block takes some getting used to. Let's do everybody's favorite lanthanide. Let's do samarium. All right, so samarium is in the D block. And you may be wondering, okay, how do we use the Nobel gas abbreviation? Because the F block is kind of disconnected from the rest of the periodic table. It's just kind of sitting there floating. How do we know where it connects? Well, the thing to remember is that the F block, so you move back over here. Row number 1 on the F block starts in between lanthanum and hafnium, right? And you know that by looking at the number, right? 58 and 57. 58 comes after 57. So you know that this section of the F block starts after you hit lanthanum, which puts you down on the 6th period, which means that xenon is your nearest noble gas with fewer electrons. If that didn't make sense to you, just look at the numbers. All right. Samarium has 62 electrons. Compare this to the two possible noble gas options. Xenon has 54. And radon has 86. We know that whenever we're doing the noble gas abbreviation, we always go with the nearest noble gas with fewer electrons. So that is going to be the noble gas we use for our abbreviation for samarium. All right, so we get ZE. Now we're down on the 6th period. We start all the way to the left. We're going to move 1, 2. So this is 6s2. Next, we're crossing over into the D. Right? So this is, if we had 6s, then we're going 5d. Now we only move one space over into the D before we hit that portal, right? After number 57, we jump to 58. So this will be 5d1. And then we jump down into the F block, which is one energy level lower than the D. So this will be 4F, 1, 2, 3, 4, 5. 4F, 5. So our electron configuration here, 6s2, 5d1, 4f5. All right, writing out our orbital diagram, we have our 6s, we have our 1, 2, 3, 4, 5d, and we have our 1, 2, 3, 4, 5, 6, 7 orbitals in our 4f subshell. So our electrons here, we've got 2 in the s, 1 in the d, and then 1, 2, 3, 4, 5. And so this will be our electron configuration and orbital diagram. Now, there's something that I want to say, and I want to say it at this moment in time. Something that you should note. F orbitals and p orbitals never steal electrons from lower shells. All right. F orbitals and p orbitals never steal electrons from lower shells. So if you were looking, if you're watching this and going, okay, when do we start like promoting because of parallel spins? That is a special phenomenon that only happens with the D subshell. All right. So you don't have to worry about it. You'll never see it show up with p orbitals or with f orbitals. So that exception only applies to the D block. Cool. Okay. All right. Let's do a couple more examples here. Okay, I see there's still people watching, but it's been radio silent for a while. So either it's been making sense and there are no questions, or it's been so confusing the nine of you don't know how to ask questions. I hope it's the former, not the latter. But if things aren't making sense, please fire off a question so I can help you out. All right, let's do another example. I know. Okay, let's do something tricky. All right, this is probably one of as far as electron configurations are concerned, this is probably the most insidious question I could throw. Let's do tungsten. Tungsten isn't specifically the hardest, but it's this type has the potential to be the most challenging. All right, so let's do tungsten. Tungsten, if you're wondering why there's a W for its elemental symbol, it's because this metal was known in the Middle Ages as it had a name, and that name was wolfram. It was named this because it's an incredibly hard metal, and it's one of the very few metals known to be deadly to werewolves. So in the Middle Ages, this is what people would use to kill werewolves, and that is why it has a W. Also, fun fact, it's also why my wedding ring is made up of tungsten carbide. That way, I wanted that. So if I ever come across a werewolf, all I have to do is punch it in the face with my left hand, and it will immolate and burn. All right. Oh, sweet. We have a question from Sarah. Let's see. Oh, are you taking questions on the exam after we're done with lecture, or do we have to email you? Okay, so real quick before we do the next example, Sarah, the answer to your question is after exam, I will be more than happy to field questions. I may not be able to answer them. I can totally answer questions that are like, I think there's a typo on problem 6. I can check it to see if there is. That's a question I can answer. If there's a question that goes along the lines of, I don't know how to start problem 6, I can't help you there. The only questions I can answer are questions that I would be able to answer if I was giving this test in class, we're all sitting in a room with 80 minutes to do it. If you came up to me for an in-class exam and asked, how do I do problem 4? I couldn't answer. But I can't answer, is this a typo, or those types of questions. But it'll be after lecture. We only have a few more examples to get through, and then we'll switch gears. Sorry, you caught me rambling about tungsten or wolfram, which I carry on my person at all times now that I'm married. All right, let's do tungsten. So it's number 74. Its nearest noble gas is xenon. So we're going to do xenon, use xenon as its noble gas abbreviation, and then we count over. Now, I'm going to do this wrong, all right? Now let me be explicit here. What I am about to do is wrong. It's wrong, but it's easy to do, so I want you to be aware of it so you avoid this mistake. All right. We can see that tungsten is on the 6th period. The wrong way to do this problem is to start at the end and go, okay, well, we go 1, 2 spaces in. So this will be 6s2, crossing over into the D block, which has an energy level that's 1 lower. So this is 1, 2, 3, 4. 6s2, 5d4. This is not the electron configuration for tungsten. And you may be watching this going like, yeah, I know that's not the electron configuration for tungsten because you have 4 electrons in your d orbital. So whenever we have 4 or 9, we're going to promote 1 electron from our s, and that way we get 5 electrons with parallel spins. But I'm here to tell you that this is still wrong. If you go, okay, well, my electron configuration for tungsten will be xenon 6s1, 5d5, which I'm proud of you for catching. The fact that we've got 4 electrons and we need to promote 1 from the s, that is correct, but this is still wrong. The wrong electron configuration for tungsten. And if you're wondering why, it has to do with the fact that in between lanthanum and hafnium, you have the entire F block. Before you can bounce from lanthanum to hafnium, you first have to bounce down to the F block. Because remember, lanthanum is 57. Hafnium is 72. Before you can go from one to the other, you have to make it all the way through your F block. All right. And so the correct electron configuration has to bounce from lanthanum down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this will be 4F14. And then from lutetium, it bounces to zirconium, 1, 2, 3. So you add another 4 to your D block. So if you're counting this correct, you would count this as tungsten is xenon. We had 6s2, 5d4, 4f14, and then you still have to correct for the fact that you've got 4 electrons in your d orbital. Sorry, not orbital, d subshell. So we need to promote 1 from the s. So the correct electron configuration for tungsten is xenon 6s1, 5d5, 4f14. All right. The orbital diagram will be long. 6s, 1, 2, 3, 4, 5, 5d, 1, 2, 3, 4, 5, 6, 7, 4f, 1 electron in our s, 1, 2, 3, 4, 5 in our d, and then 14 in our f. Whoa, that one looks kind of funky. It looks funky again. Let's just fix it like this. All right. So that is the correct orbital diagram and electron configuration for tungsten. All right. Here's the thing you've got to remember. All right, and this is what makes, I feel, these electron configurations particularly tricky. Here's something to watch out for on the, so for the, not the 5th, for the 6th and 7th periods. All right, so for the 6th and 7th periods, you have to remember that these are the 2 periods, 6 and 7, where you cross from the D to the F and then back to the D. All right, so everything on the 6th and 7th period that comes after that first space in the D block, these electron configurations No, hang on. I don't know where that ring is coming from. There we go. These electron configurations all have full F subshells. All right. Everything that comes after that first space into the D block will always have a full F subshell. So that's something to watch for when you do electron configurations. For example, let's do polonium, PO. All right, polonium is right here. It's number 84. Nearest noble gas is xenon. So we get to use xenon for our noble gas abbreviation. And you'll notice that polonium is on the 6th period, and it comes after the F block jump. All right? It comes after the F block jump. That means you'll notice a couple things. First, it'll have 6s2, right? Because you have to count 1, 2 spaces over. Because it comes after the F jump, it will have 4f14, because when you move from 57 to 72, you also jump every single element in the F block. So a full F subshell has 14 electrons. I tell you, 14 of these little arrows are hard to draw. In addition, it has polonium is in the P block, right? So to get there, we actually have to jump through the entire D block. So if we have a 6s2, this will be 5d10. And then it jumps back into the P block. 1, 2, 3, 4. So 6p4. So the electron configuration for polonium is 6s2, 5d10, 4f14, 6p4. All right, that is a long one. And the orbital diagram will be even longer. Whoops. We have our 6s, our 5d, our 4p, 1, 2, 3, 4, 5, 6, 7. Sorry, I said 4p, that's 4f. And it's 6p. Full S subshell. Full D subshell. Full F subshell. And we have 4 electrons in our P subshell. All right. So that is the electron configuration and orbital diagram for polonium. All right. Okay. So we are going to call it a day there. Let me see. Here we go. So let's call it a day. With lecture, so at this moment in time, so we're not quite done with our discussion of electron configurations. We only have one last topic to go over, which we'll do fairly quickly on Monday. Oops. There we go. So we still have to talk about writing the electron configurations and orbital diagrams for ions. But as of right now, we can open things up for exam 2 questions. Again, I don't know how useful this can be because, again, I can't really shed light on any problems. Just like if you were to ask me a question during a test, if you're struggling with problem 9 and you're like, how do I even start problem 9? I can't tell you that during the exam. Those are questions I can only answer before or after. But let's see. I know, Sarah, you posted a question about exam 2. I've not yet had a chance to read it yet, so let me take a look real quick. Okay. Let's see. So, Sarah, for lecture number 4, here, hang on one second. Let me pull up your specific exam. Wait, close. No, I don't want that. I want this. Okay, hang on. I'm just grabbing your specific test. Oh, need to look up. Oh, sweet. One moment. Please stand by. Sheets. Okay. All right, Sarah, let me see. Let me look at sent. Search sent items. All right, Sarah, I'm pulling up your version of the exam. You have a question on number 4, which I may or may not be able to answer. Okay, so let's see. So you said liquid water can be split into hydrogen gas and oxygen gas, and it's given a delta H. Okay, Sarah, unfortunately, I cannot answer your question. Yeah, totally. That's I'm not able to clarify that for you. So all I can say is look to the book, look to your lecture notes, maybe bounce some ideas off some fellow classmates, but I can't directly answer that question. Okay, Vraj, you have a question. You think there's a typo in your exam using Hess's law for finding specific enthalpy for acetic acid. Okay, let me whoops, where did that go? Again, let me take a quick look here. So let me pull up your, yeah, totally. Sorry that I couldn't be more helpful, but thanks for being cool. Okay, Raj, let me take a look at yours. Here we go. And let me take a look. All right, Raj, you think there may be a typo? Raj, I can tell you for a fact that there is not a typo. There's not a typo in problem 1. And actually, you're not the first student to ask about this. There, you have all the information you need in the problem, is all I can say. Okay, Winnie, if grades for multiple choice are really bad, will it be curved? That's an interesting question, Winnie. One that I'm not prepared to answer. But what I can say is I've never curved a test before. in my life. So probably not, because I have seen bad ones. So I would not expect a curve to happen. Am I willing to comment on the future with absolute certainty? Totally not. I have no idea what, you kind of take everything, assess everything one day at a time, one semester at a time. And this is definitely a different semester, but I would not expect a curve to happen on the exam. But I can't say for sure one way or another. But I would be surprised if I'd be surprised is all I would say. So I wouldn't expect one. Okay. So Sarah, okay, Winnie, a typo on the second equation. Sorry, Winnie, I just need a little bit, hang on. A little bit of clarification. Which equation are you? Okay, so Winnie, quick question. Which equation are you talking about? And on which problem? Okay, Sarah, does the equation list have every possible thing we need? I used Avogadro's number on a question which isn't on the front page. Is it possible that I forgot something, or should I assume I'm wrong? Great question. Okay, so Sarah, your question, does the equation list have every possible thing we need? The equation list has like all of the main stuff, but like you mentioned, you needed to use Avogadro's number for a problem and it wasn't on the front there. It's possible that there may be something that you need that's not on the front of the exam. When I wrote this equation sheet, I didn't take the same approach that I do when I write a normal equation sheet for a regular exam, because when you're taking a time test in 80 minutes, all sitting in a classroom, I need to make sure that every possible thing you need is on there. I put the big things that you will probably need on here, but I didn't go through and make sure every single thing was on there, because this exam is open book, open internet, open other humans. So if you didn't remember Avogadro's number, which is totally understandable, I haven't asked you guys to memorize it, and you needed it in a problem, you could totally look it up, like just Google Avogadro's number, just to make sure you had the right one. So that being said, the equation sheet for this test has the big picture, like general things. Does it have absolutely every specific thing? Not necessarily, because it's got because you have the internet and the textbook and all that stuff. Okay, let's see. So that's Sarah's question. I'm just taking these item by item. Winnie, how bad do test scores need to be for you to consider curving? So the answer to that question is I've never seen test scores so bad that I needed to curve them. And I've totally had classes really bomb individual exams hard. I've seen class averages on individual exams. Like there's one particularly bad one I remember where on a particular exam in a particular class, so I'm being super vague here, right? But this did happen in Once Upon a Time in a Land Far Away. There was a class that averaged like in the low 50s. I think class average was like 52% on an exam, and I didn't curve it. So I've never seen a situation so severe that it merits it. Does that mean I'm beyond considering it? Not necessarily, but I've never seen an individual test that needs it. That being said, one of the reasons why I don't I usually don't consider curving individual exams. The kind of the moment where I kind of look myself in the eye and ask, does this semester merit a curve, is not after individual tests, but it's usually at the end of the semester. So at the end of the semester, I'll look at total grades and look at the total average and ask, is a curve merited? Is it not? So I usually just tend to let the individual exams roll, and then at the end, see if things are drastically affected or not. I don't know if that makes sense, if that's comforting or disconcerting, but that's kind of my approach to it. I usually don't consider curving individual tests, but I may consider an overarching curve for the final grades at the end of the semester. Totally. Okay, so let's see. Raj, yeah, really bad, I guess. Are you willing to give more time for the next multiple choice if you see that not enough, or can this not be changed? Okay, Sarah. So Sarah's question is, how dedicated am I to the time per question ratio for the multiple choice? And Sarah, that is an excellent question. The answer to that question is I am currently 100% in so I'm in with this whole kind of electronic format, how we had to change everything mid-semester. It's definitely something that we're all still adapting to. And I think that we've been able to make the crossover and the adaptation to lecture fairly smoothly. That being said, we've had some reps with lecture, right? And this is our first example of testing in this new era. So we only have one data point. So I guess what I'm trying to say is that everything's in a constant state of evaluation and reevaluation. So, the exam scores will come in by the end of today. All of the quiz scores will be up there. By the end of today, I will have you'll have submitted all of your digital or submitted digitally all of your written exams, which I will then start grading, which will be fun and long. And after I'm done, I'll kind of sit down and I'll assess, okay, how did this go? Because this is point number one of the experiment. The reason why I selected the time, as I said on Monday, the time was chosen because it's the same time crunch that you have if you were to take the ACS final. So the amount of problems that you'd have to do would be 70. The amount of time you'd have to do those problems would be 110 minutes. So that would give you, if you were taking the official ACS final exam, you would have 1.7 minutes per problem. I'm sorry, 1.6 minutes per problem. And the time that I gave you for this quiz, you had 1.7. So you actually had a little bit more time per problem for these multiple choice quizzes. That's why I chose to scale the time like so, because it approximates the difficulty that you face for the final exam. Am I open to tweaking that time? Totally. Part of it will depend upon kind of me evaluating things out the other end once I've finished grading the written exam and kind of take a step back to look at everything. So nothing's set in stone. It may be changed in the future. It may not. Part of it depends upon how everybody does, because that helps me gauge the difficulty level of the multiple choice problem, if that makes sense. Though everybody who's been in contact with me so far seems to indicate that the time crunch was real, which I warned about, but it seems to be hitting very hard. So we'll see. Okay, sorry, that was a very long-winded answer to the, are you willing to give more time for the multiple choice? Okay, moving down. Okay, Winnie, you said equation 2. Is there a typo in equation 2 for Vraj's question? Winnie, there is not a typo for equation 2 in Vraj's question. Just looking at it real quick. Nope, no typo. It's good. Let me just add this to the text thread. no typo equation 2 in Raj's. Okay, moving on down. Okay, Sarah, is it cool if we send you an email after we submit the exam to confirm that the quality is clear? Okay, yes. Okay, Sarah, excellent question. What about quality? So here's, yeah, I totally understand being paranoid about that because I don't take late submissions, blah, blah, blah. So for exam, I don't know why I just wrote an L. Written exam, photo quality. All right, that is, Sarah, a great question. Because if the photo quality is bad, I won't be able to grade it. And I don't take late submissions. Here's the thing. If the photo quality, if the photo quality is too poor to grade, and again, I've only seen one example so far, and it was totally fine, totally gradable. To grade, I will request a resubmission. So what I'm going to do, like I said, I've got one and it was fine. But as people are submitting their exams, I'm going to be opening the files to make sure I can read them. And if it's a little mushy, I'll send you an email requesting you to send me a better picture, or maybe a scan, if you can. And if I do that, I'll be able to compare the two side by side. So I'll know if you've written additional things or changed the work, because even if it's too mushy to grade, I'll still be able to like low key read it. So if the test has been altered, that's cheating. Don't do that. But, if you just take a better picture, cleaner picture, better lighting, or maybe a scan of the what's the word I'm looking of the test that you already sent in, that'll be totally fine. So Sarah, don't worry. And because there are 50 of you, I'm not going to send an email that says it's okay. You'll only get an email from me if I need a better picture quality from you. And if I do request that, you will not be docked points. So hopefully that relieves the tension, the paranoia that you're feeling. Hopefully that answers your question. Also, do you want us to only submit photos, or can we put the pics in it? Oh my goodness, Sarah, that is another great question. It would be awesome if you put your pictures in a document. Like, I can't even tell you, Sarah, if you put your pictures in a document, that would be rad. That would be so stinking awesome, because it would simplify my life a ton. So I would greatly appreciate that if you wanted to submit it in that format. Okay, Winnie, you're next on the stack. Will we be getting extra credit on our exams anymore since we did on the first exam? Excellent question. Excellent question. And okay, so Winnie, you're asking about the extra credit, how I normally so my exams are 120 points each, but there's usually 130 points available. And so so I had every intention of so my plan was to make the multiple choice worth 60 points, and then the take home exam was going to be worth 60 points, and then but I was going to make the take home exam actually worth 70. And as everybody knows, because you're all currently holding the take home exam in your hands, there's only 60 points on the take home exam. So there's technically no extra credit points on exam 2, but I'm still going to give out some extra credit points, so everybody's going to receive a little boost of points for doing nothing, because I'm the one who forgot to put the extra credit on the test. So hopefully that makes you all feel a little warm and fuzzy inside. Okay, but where am I next? Okay, that was Winnie's extra credit problem. Vraj, people whose, let's see, the first time taking the Canvas style exam, the exam was not hard, but the format. Okay, so hang on, I'm trying to. Okay, so so I guess, Raj, your question, and correct me if I'm wrong, but it seems like your question is, will the fact that the Canvas style testing is a new style be taken into account how it's graded? And the answer really is no, because I don't grade the Canvas exam. Canvas does. So the answers are, it's just multiple choice. You either selected the correct one or one of the 4 wrong ones, and that's what determines whether you earn the 2 points on that problem. So it won't be, because it's right or wrong. It's you got it right, you got it wrong. So the multiple choice exam is kind of just, it is what it is. Peter, the time crunch was real and broke your neck. I am so sorry to hear that. That part about your neck. I would recommend the following prescription. This is how I would move forward in the future. Okay, Sarah, which version of the test had a typo? It wasn't mine, correct. The version of the test, so there's one version where there was a Hess's law problem that had 3 equations, and the third equation had H2 plus N2 going to what should have been NH3. But the typo on the exam was, it just was written NH. So if you have that version of the exam where the last part of the last equation in the Hess's law problem had H2 plus N2 going to NH, the correction is NH3. So if you have that one, then there is a typo. And if not, there wasn't. Sorry, I don't remember yours off the top of my head, but I don't believe yours had. I believe you had the one with aluminum. Okay, Winnie, you got an email, yes, saying that your test had a typo, and then an email saying there isn't a typo. Is there a typo in your version? Winnie, there is not. So last night, when I realized that there was a typo in some of them, I went through and started emailing everyone with the typo, but it was also late, and I got overzealous and just was mindlessly sending the email. And then I sent the email to some people who didn't have that version. So I sent the corrected email saying, nope, sorry, not a typo in your version. So when you're in the clear, I sent you a correction email, an error, and then sent a correction email to correct the errored correction email. That was confusing, but you're good. Okay, Sarah. Okay, let's see. Wait, can you answer the second part of my question? The file types. It's just 10 points, please. B10 lol. The file types. Okay, second part of your question. Okay, Sarah, sorry, I'm just getting to it. Oh, yeah. Okay, sorry. What file types am I cool with? I am cool. Okay, sorry, yes. Sarah, doops. PDF. Doc. X. Though I would say that PDF is my favorite. That's my new favorite emoji, courtesy of Raj from a couple lectures ago. Okay, let's see. Wait, can you answer the second part? Is it 10 points? Okay. Oh, for the extra credit. Yeah. So Sarah, to answer your question, and then this kind of dovetails back on Winnie's with the extra credit. Because I forgot to build an extra 10 points of extra credit into the take-home exam. There's actually a couple ways that I could allocate the extra credit points. And I haven't decided yet. So I'm still kind of turning it over in my mind how exactly I'm going to dish those out. So I'm not ready to comment yet. But I will let you all know more in the future. All right. Other questions, concerns? We still got 6 people hanging out, which is actually a lot more than I thought there'd be. I thought today would be a ghost town. I thought I'd be talking into the microphone like by myself, and then at the end, some people would poke their heads up and ask questions. But you guys hung out, which was cool. I'm glad to see that that some of you are still alive and even willing to talk to me, even though you're currently under the duress of the second exam. I'm sorry to hear about Peter's neck. I hope that gets better. And again, if you listen to Protect Your Neck by the Wu-Tang Clan, it will definitely help in the future. Are there any other questions before I go? Let's see. I was impatiently waiting till the end of lecture. Seriously. Oh my gosh. Sarah, you're like, come on, wrap it up. We got peeps. We got questions to talk about. There's an exam on the line. Well, thank you. Even though you were impatiently waiting, thank you for waiting. And I know that I can't be as useful as I'd like to at this moment in time. I guess this is worth mentioning as well. Don't forget. Oops. this Friday, at 1 p.m., we have office hours. I will still be holding them, and the beauty of office hours this Friday is the exam will be over, which means I can answer any question in explicit detail. Actually, I should qualify that. I can't answer any question. During office hours, I won't be able to answer questions like, if I made this mistake, how many points will I lose? I don't know that till I actually sit down, write a rubric, and grade that problem. So I won't be able to comment on, like, I messed this up, what's my score going to be? I won't know, because I won't be done grading by that moment in time. But I can answer questions like, okay, problem 4 on my test was super gnarly. How do you do that? Can you show me step by step how to work through it? I am more than happy to answer those types of questions. So as unhelpful as I've been on this side of the exam, I will be able to be the equal and opposite of that on the other side once things are submitted tonight. Also, any questions like that that you submit over email, I'll most likely hold and comment on during Friday's office hours, mostly because if I do them in office hours, they'll be more they'll provide the most help to the most people, because bottom dollar says if you have a question, then everyone on a problem, everyone else who had that question on their take-home exam also has the same question, so we can reach the most people. If I post it during a stream rather than answering your email directly. Cool. So if we're out of questions, we'll go ahead and conclude this stream. Thank you everyone for showing up. It's been wonderful seeing your bright digital faces. Hopefully they're not too sleep deprived. As of this moment in time, it looks like you've got about 10-ish hours to finish this thing. And so I wish you all the best. I want you to win. And I am looking forward with fear and trembling to grading them all. Cool. All right. I will see you guys Friday. Thanks for stopping by. And happy April Fool's Day.